Now, we're going to be starting with multi-level queue. The idea behind multi-level queue is to classify tasks, okay, based on priority or type, by the way. So the first queue could be something like like operating system processes. Okay, this would be something like administration. Okay, this would be like something like user, or you know what I'm saying? So different types or priorities. So the coming process to the system, if it's priority 0, it will go here. If it's priority 1, it will go here, and so on. Now, of course, priority 0 will execute before priority 1, and so on. So if you have something like that with a single processor, what's going to happen is this processor will be dedicated for priority 0 queue. When priority 0 queue is done, it will go for priority 1. Okay? While it's serving priority 1, there is a process that arrives to priority 0. So now the processor will leave priority 1 and go back to priority 0, serve it and go back to priority 1, and so on. So for this approach, the multi-level queue, we classify processes based on type or priority. Type or priority. The other one, so it works like this, you see here. So as an example, here you have real-time processes, system process, interactive, batch, whatever that is, you know. Priority goes higher this way, lower the other way, okay? And each and every one of them would have, you know, certain, like, you know, separate queue. The other one is called multi-level feedback queue. And the multi-level feedback queue, it actually classifies based on burst. Based on burst, okay? So what happens here is as follows. Assume that we have those 3 queues, 1, 2, 3. So the first queue is assigned a quantum, okay? Of course, I mean, the author here says it's a round robin. It's not round robin, really. Okay, I disagree with this totally. It's not round robin. Okay, because round robin means, you know, you give the quantum and then you have to put it back to what it is. This is not the case. The process takes a quantum. So let's say here you have a process with the length of, let me, here. So process 1, you have a length of 20. Process 2, you have a length of 14. Process 3, you have a length of 9. Process 4, you have a length of 5. Process 5, you have a length of 1, as an example. So process 1 will go to this quantum. The quantum here is 8. So P1 will be processed here for 8 time units. And I'll come to this queue with a time of 12. Why 12? It was initially 20, and you processed 8, so the remaining is 12, okay? The second one is 14. You would take 8, so P2 here would be 6, okay? You have P3, go here, take 8, so P3 is gonna be a 1. P4 and P5 will take the quantums and leave. So P4 and P5, they get out of the system from the first stage. The second stage, you have P1, P2, P3. As you can see here, the quantum is 16. So all of them will finish in this stage. Assume that I have here P6 with something like 40. Quantum is 40, okay? So P6 will come here with 8, so it's gonna be here, P6 will be here with 40 minus 8, that's gonna be 32. Here, out of this, P1 is 12 and the quantum is 16, so P1 will leave. Sorry. Okay. P1 will leave here because it needs 12 to finish and the quantum is 16. P2 will leave. P3 will leave because P3 also, and it's just 1 and the quantum is 16. And P6 will work with the 16 and go here with another 16. So here P6 with 16. Why? Because it was 32 and the quantum is 16. 32 minus 16, the remaining is 16. Here it goes to the last level. It has to be non-preemptive. The author says it has to be first come, first serve. It's not true. Any non-preemptive algorithm would work. So the process here goes to this one. It's guaranteed that it will get out. Okay. All right. Of course, the first come, first serve is favored because it would never cause starvation. If you use shortest job first and you have many processes here waiting and the processes keep coming and one of them is huge, it would have starvation, right? So that's why first come, first serve is favored. But if you use shortest job first, what would you use with it? Aging, right? Aging. Okay, so that would solve the problem. All right, here it is. That's the multi-level feedback queue. We're going to be skipping those. And we're going to go for, just talk about the load balancing. The idea behind load balancing is that you have load that is coming if you have multiple processors. Okay, so processor 1, processor 2, processor 3, processor 4. If you have a load balancer here, the load balancer will actually distribute work among those processors to make sure that the load is balanced. You wouldn't have one processor that has a load of 6 hours of work and the other one have few minutes. No. Now, you would say, okay, let's divide it. Well, there is a huge difference between dividing it and balancing it. It's very hard to divide it, but it's easier to balance, okay, and faster to balance, all right? So we do balancing. So as an example, I have here 10 hours of work. You have here 5 hours of work. You have here 8 hours of work. You have here, let's say, 9 hours of work. If you have work for 6, the logical one to be to assign it to is this one. So this is going to be 11, to keep balancing the load this way. Okay, and then we're going to go for real-time CPU scheduling.